We will now have the continuation of our discussion, starting with the short circuit. So when I say short circuit in graph theory, actually, short circuiting, what we do is we combine or merge vertices while maintaining all the connections. Okay, so it could be two vertices or points. When I say vertices, these are also called as nodes or points. Okay, so it could be two, it could be three, or it could be more. Now, here we are going to combine our W, Z, and X. Okay, so this is our W here, Z, and X. So maybe we can put it here. W, Z, and X combined together. And this is our Y here. Okay, so originally we have only 4 points. Since we combine 3 points, the remaining are only 2 points. Okay, because here we have 3 plus 1 is equal to 4. That is how to check whether you miss anything. Okay, so we can start with A. Our A is from W to Z. So W and Z or Z are together. So it's gonna be a loop. That is our A. Our B is from W to X. Again, W and X are together. So gonna be the second loop. Okay, that's our B. Our C is X to Z, and X and Z are together. So we're going to have our third loop here. This is our C, right? So we don't have D, we don't have E. Okay, we have F, that is from Y to Z. Y to Z, our Z is here. And our G is W to Y. Again, we need to create a multiple edge here. And our H is from Y to X. So we need to create our third multiple edge. Okay. So all in all, we have 6 edges. We have 3 loops and we have 3 multiple edges. If we're going to check here, we have also 6 edges all in all. So we did not lose any edge actually. We just created a shortcut. Instead of traveling to W, X, and Z, we just created one point here. Okay, so from Y to W, we can easily travel, and from Y to Z and Y to X as well. So that is mainly the purpose of short circuiting, to save time, to optimize processes. Points, of course, because we are merging or combining some of the points. Let's proceed to the complement. Okay, we are done with short circuiting. When I say complement, actually, usually when we talk about complement, we talk about simple graph. So this means that we don't have loops and we don't have multiple edges or parallel edges. When I say complement, it is the opposite of the original graph. Okay, opposite of the original graph. So this is our original graph. We call this as our G, for example. So Our G complement is G bar in graph theory. This means not G. Okay. G bar means not G or complement of G. Okay, so we call this as complement of our original graph. Right, so now the first is to actually label all the points. That's the first step when you are drawing the complement of any graph. So this is our V1, V2, V3. This is our V4, and here is our V5. So this is how to actually start our complement. We have to label all the points, and we have to draw the opposite. So as you can see, our V1 is adjacent to 2 and 4. The opposite is 3 and 5. So either you can do like this or you can do like that. It's up to you. Okay. So V1 is adjacent to 3 now and 5. Originally, it's V1 to V2 is now deleted, and V1 to V4 is deleted because it's the opposite. Okay. Now, our V2 is actually adjacent to 3, 1, and 4. The opposite is only 5. Okay. So only 5. And our V3 is connected to 2 only. It should be connected to 1, 4, and 5. It is connected to 1 already. We don't need to draw it again. So we have to draw V3 to V4 and V3 to V5. Our V4 is connected to 2 and 1. The opposite is 3 and 5. It's connected to 3 already, so we have to connect only V4 to V5. Okay, our V5 is not connected to any of the points because it is isolated. Now it is connected to all the points, V1, V2, V3, and V4. So we don't need to draw it again. So this is basically our answer. This is the complement of this original graph. This is the opposite of G. Okay, so that's how to do it. I want you to rewind, forward the video, or pause the video for you to understand better. Okay, here you're going to find the 11th term of this sequence. Okay, so we have to find, I could not see properly. Okay, we have to find our A and R. Find the 11th term of this sequence. The formula is given. The formula is A times R raised to the power of n minus 1. This means that this sequence is geometric sequence. Whenever we have R, we're talking about a geometric sequence. So basically, we have to find our A. Our A is the first term, that is 1, and our R is, of course, the second divided the first term. So negative 3 divided by our first term is 1, so the answer is negative 3. The question is to find the 11th term. It means we have to change our n to 11. A is 1, and our R is negative 3 raised to the power of 11 minus 1, because our n should be equal. So this is 11, so this should be 11 here as well. So our A sub 11 is 59049. Okay, that is the 11th term. So this is very simple. The formula is given. You just have to find A and R and plug in the values, use the calculator, you get the answer. Okay, so that is number 14. Our answer is actually 59049. All right, let's proceed to number 15 now. Number 15, actually, you are going to find the sum of the first 16. We call that a series. Okay, sum of terms actually is called a series. Okay, so here the formula is given. That is S sub n. S here is series sum of number of terms. We have A times the quantity 1 minus R raised to the power of n over 1 minus R. Okay, so you have to find A and find your R. So A is 4, very simple, the first term, and our R again is the second divided the first. That is 12 by 4 is equal to 3. Our second is 12, our first is 4. Okay, so our A is 4, our R is 3, our N is 16 because we're going to get the sum of the first 16. So we have to plug in all the values. Our A is 4 and our R is 3. So this becomes 3 and N is 16. Because first 16 and this is 1 minus 3. Because our R is 3. So we have to use R 2 times. We have R here and R here. So these two numbers are equal. Then we have negative 2, that is 1 minus 3. Use the calculator. That's the answer. Actually, it's 86,093,440. That is the sum of the first 16 of this sequence. Right? So I guess this is very, very clear. Let's proceed to number 16. Number 16, you're going to find the first three terms and the common difference. So the words common difference or D, okay, is there. So it means this is about arithmetic sequence. And the partial sum is the arithmetic series. Okay. All right, so the nth term is given. This is the nth or the general term. That is a sub n equals 4 minus half or 0.5 of n. So basically our first term is 4 minus 0.5 times 1. Okay, because we change our n to 1, this will also be 1. These two should be equal. So 4 minus 0.5 is, of course, 3.5. And our a sub 2 is 4 minus 0.5 times 2. We change our n to 2. So this will be 3 because 0.5 times 2 is 1. And the third term is 4 minus 0.5 times 3. We change our n to 3. So this will be 2.5. As you can see, our numbers are decreasing. From 3.5 becomes 3 and so on. So our D, our common difference, will be also negative because this is going down. Our A sub 2 is 3 minus A sub 1. That's the formula for the common difference or D. So negative 1/2 or negative 0.5 is the answer. Now the next is to find the 19th partial sum. So to find the 19th partial sum, we have to use the formula. Formula is given. We have n over 2 times the quantity of a sub 1 plus a sub n. So we are going to change, when I say partial sum, most of the series actually when we are talking about series or sums of the terms, most of them are partial only. We cannot add all because it will keep on going. For example, here we have a sub 1, a sub 2, a sub 3. We can also get a sub 4 until infinity. So this is only partial actually what we're adding. We cannot add all. So this will become S sub 19. That's the meaning of 19th partial sum. It means find the S sub 19. So this will become 19 over 2. A sub 1 we have already. It is 3.5 here. Plus we don't have A sub n. Now our A sub n, that is A sub 19. That is 4 minus 0.5 times 19. Yeah, using the same nth term, the given. Okay, so A sub 19 equals 4 minus this, negative 5.5. Okay, 4 minus 0.5 times 19. So this is negative 5.5. So S sub 19 will be negative 19. Okay, why negative 19? Because you can use your calculator anyway if you want to. Because 3.5 plus negative 5.5 is negative 2. Negative 2 divided by 2 is negative 1. Negative 1 times 19 is equal to negative 19. Okay, so that's the answer. Let's proceed to number 17 now. Number 17, actually, we have here changing from symbolic logic to English sentences. When I say formal statements, we talk about predicate forms. Yeah, the symbolic logic. And when I say informal, we talk about the English sentences. Okay, so please remember this. English sentence or sentences are informal. The symbolic or the predicate forms are formal statements. So these are symbolic. We use symbols, variables and inequalities, equations, and we're going to change to English sentences. The first one here is for all x, element of R, x cubed is greater than negative 1. So please memorize this. R means set of all real numbers. When I say n, natural numbers or counting numbers. Q, of course, rational numbers. Okay. Z, integers. Right, so here the answer is starting from all, or you can use every. All, because of this, it means universal quantifier. Okay, when I say universal quantifier, all elements are included. All, then we have elements, so x here. So this is for all x in R. So this means element of. So it means in or inside. Okay. So it means that this x here that we are having here, this the subscript actually, okay, it's like below this universal quantifier, means x here is any of this. That's the meaning of that. Comma, x here is raised to the power of 3 greater than negative. It means that all real numbers have cubes. because we have 3 greater than -1. Okay. If it was x squared, you're going to say squares. Okay, greater than 3, like x to the 4th, x to the 5th, you just say powers of. Okay, so if it was x to the 10th, you say powers of 10. This is x raised to the power of 20, powers of 20. Okay, so this is the answer. All real numbers have cubes greater than -1. You can use singular. You say every real number has a cube greater than -1. It's up to you which one you're going to use. You can use the plural like this, or you can use the singular. But it's always easier to use the plural form, all. Okay? All right, so let's proceed to number 2 now. Number 2 here we have this. There exists x in z plus, comma, or such that x squared is equal to 4. So how do we change this? So whenever we see that symbol, we can use sum, we can use there exists. Okay, so number 2, we have this symbol in z plus such that, usually say such that, or you can use directly, whose. Okay, so here we have x squared, so we can use squares. So sum is easier to use the plural. So this, we use sum, there exists, okay, somebody, someone. These are the keywords, okay? So sum, positive integers, because we have z plus, z means integers, have squares equal to 4. You can also say there exists a positive integer if you're going to use there exists. So you can also say there exists a positive integer. It's going to be singular now because you use the words there exists, such that its square is equal to 4. So you can such that its square is equal to 4. Or you can say there exists a positive integer whose. So you can change this to whose square is equal to 4. It's up to you. You can use the singular or you can use the plural form. But choose only one, okay? No need to show the plural and the singular. Use only one. Let's have the third. The third one, if you have this symbol, you can use if. So if it is an elephant, then it has 4 legs. So you can use if then. This symbol means if then statement. This is if then operator actually, or conditional. We also call this as conditional operator because we have a condition. Okay, here our condition is if it is an elephant. That is our condition after if. You can also say, see, we have this, x is an elephant, then x has 4 legs. So here you can use the plural. You can say all elephants have 4 legs. This is also correct using the plural form. Directly, you can use all elephants have 4 legs, which is shorter and easier. Okay, so you can use this as your final answer. So let's go to number 4 now. Okay, number 4, here for all x in R, if x, comma, if x element of n, then x, okay, element of Q. Now, if there is if in the middle, you have to start from there. So your answer will start with if, then go to the left, and then go to the right. So if a real number is a natural number, go to the right. That is your n. This is your n. This is your r. Okay, from here. Then it is a rational number. Okay, that's how to translate that into English sentence. If, go to the left, a real number, is a natural number, and then it is also a Q, rational number. Okay, so this is how to translate from symbolic or from predicate form to English sentence or informal form. All right, let's proceed to number 18. This is the opposite. Here we have the English sentences. We will change to the predicate form or the formal form. Right, so let's answer number 1. Number 1, some animals fly and talk. So this is our predicate here. This is the predicate. This is our subject with a quantifier. This is the quantifier. There exists. Some means 2 or more, but not all. Okay? So that's the meaning of that. So some animals fly and talk. So we have to separate. This is our subject here with a quantifier and our predicate, okay, from fly until talk. So the answer will be starting with this symbol because of some. And then we put our x here, subscript. And then we have open. We have to define our domain. This is our domain, what we're talking about. So x is an animal. For animal, open and close x. Actually, we start reading from here. So basically what we do is to define this, is defining this. What is this x here? This x here could be any letter actually. It can be M, it can be N, any letter. But usually we use x. Now, this is our predicate from fly and talk. We have to have here a connector. And it means that we are splitting now. This is the subject here. And here we have the predicate, okay, on the right. So we have to open. That means the whole group for the predicate. We start with the first fly. So it means that our x, okay, whatever we're talking, this is an animal. Okay, x here is animal. This x flies, but we use the base form of the verb. The base form of the verb. And here is this symbol. And then we have talk, open and close x. So x flies, x talks. Okay, so and is this or is this? So please remember this. So we have to close this, and we have to close also that towards the end. So that is our answer. So this is the answer from here until here. So it means some animals fly and talk. So we are changing from English to symbolic form or predicate logic, predicate form. All right. So I hope this is very clear. Let's go to number 2. If someone cries, he is sad. So here we have if then. Sometimes we remove then, we just put the comma like this. Comma, he is sad. Actually, it means here if someone cries, then he is sad. Okay, in some cases we remove then, it is understood. So for number 2, we have if, so the keyword is someone. Someone cries, then he is sad. Guys, we don't know whether this is true or false. We don't look at the truth and the falsity here. We are just converting. We are not looking at this. Okay. Now, the answer will be starting from there exists because of someone. Okay. And then we have to define that someone, person. So X is a person. This X here that we're talking about. And a cry. So X cries, but we use the base form again. Okay, please take note. The base form of cries is cry. Dances, dance. That's the base form. Okay, then because of if, okay, X is sad. So we have to close and close. Okay, so if a person cries, then he is sad. X here is the he or she. Okay, that person. All right, so that's how to answer the second one. The third one is no horses have wings. So how to change this into symbolic form? Number 3, no horses have wings. The first step here is to change this to all. All horses, transfer no to the middle, do not have wings. Okay, that's the meaning of no horses have wings. It means that all horses do not have wings. So we let H equals set of all horses. This is the first. You have to define first the domain. What is the domain? What we're talking about. Okay. So our answer here, we start with this because of all in H. That's like, you know, that's the horses. All horses. Comma X singular does not have wings. Okay. So always we have to convert to the singular form when we are converting to the predicate logic or predicate form. So this means that every horse does not have wings because X here actually is singular, like every X part of this whole. So X here could be any horse. Okay, X is an element E of this H. So it belongs to this H. So that's why X does not do not, because we make it singular. Okay, let me give you one more example here for you to understand. For example, when we say all human beings, all humans, are mortal. Here we don't have not or what, so or we don't use no. So we let age equals set of all humans or human beings. So our answer would look like this. This because of all in H, comma, X is mortal. So we use is, not are, because again, we have to use singular because it's every X. Okay, so let's have number 4. All students except Mariam dance. Okay, this one. Now, here it means that if the student is not Mariam, then that student, he or she, dances. So this is except, not equal to. Okay, so not equal to is except Mariam. Okay, so I'm going to put the answer here. We're going to start with this because all students here. And then we have to define our domain. X is a student and X is not equal to Mariam. Then X dances. Okay. So this means that all students except Mariam dance. Or if a student, because we have if then here symbol. If a student is not Mariam, then X, he or she dances, or that student dances. Okay, so that's the answer here. I have answered all these questions. I want you to, again, go back to this recording later and try to master how to do this. Number 19 is just to define what is inductive and what is deductive reasoning or argument and give examples. So deductive reasoning actually is top-down approach. When I say top-down, we start from general and then we proceed to specific conclusion. So it is from general to specific. So it takes premises. So basically we say it takes premises and reduces them down to a specific conclusion. That is deductive argument. We're going to start with premise 1, premise 2, and then the conclusion. So all men are mortal. Ali is a man, therefore Ali is mortal. This is an example of deductive argument or deductive reasoning. The inductive reasoning is opposite. Instead of top-down, we say bottom-up approach. So from specific to general. So it begins with a specific argument, arrives at a general logical conclusion. So we cannot tell whether it is true or false. We can just say strong or weak. For example, here, every time you eat peanuts, you start to cough. And then you are saying, you are generalizing, you are allergic to peanuts. This is the general. And this is the specific here. So from specific to general. Your conclusion is based on your observation. Right? So I have given you many examples before of inductive reasoning in our classes. So please go back to them for you to recall. Okay? Let me give you another example of inductive. Let's say I put 7 frogs in the fridge for 1 week, and they died. And then you conclude, therefore, all frogs die when they are put in the fridge. Guys, this is just an example. Don't do this. Okay? I'm just trying to give you a specific here for you to understand. So this is like an experiment. You put 7 frogs in the fridge for 1 week and they died. Therefore, all frogs die when they are put in the fridge. So here is our conclusion. General. Specific 7 frogs, general all frogs. Yeah. So it is an example of inductive argument. All right. So number 20, the last one, is about walk. So what is an open walk? What is cycle? What is a path, trail? Yes. Or let's see close walk. Okay, you know close walk already. It means we have to come back. So open walk, any movement on the graph actually. Okay. Any movement on the graph where you can repeat vertices and edges several times or many times for as long as you want, but you should not come back. Okay. So V1 is not equal to the last vertex. Okay, that's the first one. It's open. Okay, so vertices and edges can be repeated for n number of times. Okay, so you can also use this definition. That means you can repeat the vertices and the edges n number of times for as long as you want until infinity. Okay, so you can also say it is a movement from one point to other points where the first vertex is not equal to the last vertex, and vertices and edges can be repeated until infinity. Okay, so an example of this, so you have to give an example. You can start from V1, E7, V4, E7 again, V1, and E5 and V3. Okay, so I started with V1, okay, and ended here, V3. So from here, this is the end. So it's open. I did not come back there. And I repeated E7, and I repeated V1. Okay, V1, E7, V4, E7, again, V1, E5, and V3. Okay, so I hope that's clear. That's an open walk. You can make the definition simple as long as it is understandable. Next is path. Okay, path, very simple. It is open and vertices and edges cannot repeat. So it has a very simple definition. Path is the simplest of all. Vertices and edges cannot repeat. You just have to continue. So you can start with V3, for example, E3, V2, E6, V4, E7, V1. So it's open. I started from V3 and then ended here, V1. And I did not repeat anything. V3, E3, V2, E6, V4, E7, V1. So somehow it's like this. Then move like this until here. So that is an example of a path. You don't repeat anything. Okay, let's have the cycle. Cycle is a closed path. So we can close this directly actually by doing like this. It will become a cycle. So cycle is closed. Vertices and edges cannot be repeated. Okay, except the first and the last. First and the last vertices. Okay, of course, because we have to come back. Okay, for example, we started from V3 and E3, V2, and then we have E1, you can do like that, V1, E5, V3. So from V3, then E3, V2, I took E1, V1, then E5, V3 again. So that is a cycle. Okay, except the first and the last. In between, we don't repeat. E3, E1, V2, V1, E5. That is a cycle. Okay, so it's closed. Vertices and edges cannot be repeated except the first and the last vertices. Let's have the trail. Trail is open. Vertices may repeat. But edges cannot repeat, of course. Okay, so an example of that is V1, E1, V2, E4, V2, then E6, V4. This is a trail. I started from here, then E1, V2, then the loop, then V2 again. So I repeated V2, but I did not repeat any edge. Then E6, V4. So we have E1, E4, E6. Okay, so no edges repeated, but we repeated some of the vertices here. Of course, the circuit is a closed trail. Okay, let's fix that. So here we have vertices may repeat, same above, edges cannot repeat. Okay, so we can close this actually. We can have V1, E1, V2, E4, V2, E6, V4, E7, V1. This is an exact example of a circuit. V2 repeated. Okay. Of course, V1 repeated because we have to close it. But we did not repeat any edge. We have E1, E4, E6, E7. So we just close our trail. So a circuit actually is a closed trail. Okay, so that's all. I have discussed all the revision topics. So I might be adding one more video, especially regarding the predicate logic, for you to master the concept. Okay, so thank you so much for watching. Until the next time, bye bye.